Hi students, now we have discussed about corrosion and its control. So corrosion is the metals and alloys are generally used as fabrication or construction materials in engineering. That metals are destructed is due to some environmental reactions, that is the corrosion. If the metal or alloy structures are not properly maintained, they deteriorate slowly by the action of atmospheric gases, moisture and other chemicals. This phenomenon of deterioration or destruction of metals and alloys are known as corrosion. So corrosion is defined as the gradual destruction of metals or alloys by the chemical or electrochemical reaction with its environment. The causes of corrosion. Metals occur in nature in two different forms. One is native state, second one is combined state. Native state, that means metal occur in native or free or uncombined state or non-reactive with the environment. They are noble metals exist as such in the earth crust. They have very good corrosion resistance. For example, gold, silver, platinum. In combined state, except noble metals, all other metals are reactive and react with environment and forms stable compounds as their oxides, sulfides and chlorides, carbonates. They exist in their forms of stable compounds are called ores and minerals. For example, Fe2O3 ZnO and PBS and CaCO3, etc. How and why corrosion occurs? The metals are extracted from these compounds are known as ores. During the extraction, these ores are reduced to their metallic states. In the pure metallic state, the metals are unstable as they are considered in excited state, that is higher energy state. Therefore, as soon as the metals are extracted from their ores, the reverse process begins and form metal compounds which are thermodynamically stable, that is lower energy state. Okay. The corrosion diagram is shown in figure. Metal is react with environment, that means a layer of oxide formed on the metal surface. The reaction is known as corrosion. Hence, when the metals are used in various forms, they are exposed to environment. The exposed metal surface begins to decay, that is conversion into more stable compound. This is the basic reason for metallic corrosion. So due to corrosion, some useful properties of metals such as electrical conductivity, ductility and malleability, etc. are lost. Then consequences of corrosion. Due to the formation of corrosion product over the machinery, the efficiency of the machine gets lost. The products gets contaminated due to corrosion. The corroded equipment must be replaced frequently. And plant get failure due to corrosion. It is necessary for over design to compensate for the corrosion. The corrosion releases toxic products, health hazard, etc. In classification or theories of corrosion. Based on the environment, corrosion is classified into dry or chemical corrosion and wet or electrochemical corrosion. Dry or chemical corrosion. Dry corrosion is due to the attack of metal surfaces by the atmospheric gases such as oxygen, hydrogen, sulfide, sulfur dioxide, nitrogen, etc. There are three main types of dry corrosion. One is oxidation corrosion, second one is corrosion by hydrogen, third one is liquid metal corrosion. So oxidation corrosion. Corrosion by oxygen or oxidation corrosion is brought about by the direct attack of oxygen at low or high temperatures on the metal surface in absence of moisture. For example, alkali metals, lithium, sodium, potassium, etc. Then alkaline earth metals, magnesium, calcium, tin, etc. are rapidly oxidized at low temperature. At high temperature, almost all metals except noble metals, for example, gold, silver, platinum, are oxidized. So, mechanism of dry corrosion. Oxidation occurs first at the surface of the metal, resulting in the formation of metal ions N2 plus, which occurs at the metal oxide interface. So M thus forms M2 plus 2 electrons. Then oxygen changes to ionic form O2 minus due to the transfer of electron from metal, which occurs at the oxide film environment interface of O2 plus 2 electron. This forms O2 minus. So oxide ions reacts with the metal ion to form the metal oxide film. M plus of O2 thus forms M2 plus O2 minus, thus forms metal oxide film. Once metal surface is converted to a mono layer of metal oxide for further corrosion, oxidation to occur. The metal ion diffuses outward through the metal oxide barrier. Thus, the growth of oxide film commences perpendicular to the metal surface. The diagram of dry corrosion by oxygen is shown in figure. Nature of oxide film. The nature of oxide film is formed on the metal surface plays an important role in oxidation corrosion. Stable oxide layer. A stable oxide layer is a fine grained in structure and gets absorbed tightly to the metal surface. Such a layer is impervious in nature and stops further oxygen attack through diffusion. Such a film behaves as a protective coating and no further corrosion can develop. For example, oxides of aluminium, tin, lead, copper are stable oxide layers. In unstable oxide layer. Unstable oxide layer is mainly produced in the surface of noble metals, which decomposes back into the metal and oxygen. The metal oxide thus gives metal plus oxygen. Oxides of platinum, silver, etc. are oxide layers. In volatile oxide layer. The oxide layer volatiles as soon as it is formed, leaves the metal surface for further corrosion. For example, molybdenum oxide is a volatile. Then protective or non-protective oxide film. According to Pilling-Bedworth rule, if the volume of the oxide layer is formed less than the volume of the metal, the oxide layer is porous and non-protective. An example, the volume of oxides of alkali and alkaline earth metals such as sodium, magnesium, calcium, etc. is less than the volume of metal consumed. Hence, the oxide layer formed is porous and non-protective. On the other hand, if the volume of the oxide layer is formed greater than the volume of the metal, the oxide layer is non-porous and protective. The volume of oxides of heavy metals such as lead, tin, etc. is greater than the volume of the metal. Hence, the oxide layer formed is non-porous and protective. In pilling Bedworth ratio, the ratio of the volume of the oxide formed to the volume of the metal consumed is called pilling Bedworth ratio. Corrosion by hydrogen. Hydrogen embrittlement at ordinary temperature. When metals contact to H2S at ordinary temperature causes evolution of atomic hydrogen. So Fe plus H2S, this forms FeS plus 2H. This atomic hydrogen diffuses readily into the metal and collects in the voids where it recombines to form molecular hydrogen. Collection of these hydrogen gases in the voids develop very high pressure which causes cracks and blisters on metal. Thus, the process of formation of cracks and blisters on the metal surface is due to high pressure of hydrogen gas. It's called hydrogen embrittlement. So, decarburization at high temperature. At high temperature, atomic hydrogen is formed by the thermal dissociation of molecular hydrogen, H2 in the form of heat. This forms 2H. When steel is exposed to this environment, the atomic hydrogen readily combines with carbon steel and produces methane gas, C plus 4H. This forms methane, CH4. The collection of these gases in the voids develop very high pressure and causes cracking. Thus, the process of decrease in carbon content in steel is termed as decarburization of steel. And third one is liquid metal corrosion. This is due to the chemical action of the following liquid metal at high temperature. The corrosion reaction involves either dissolution of a solid metal by a liquid metal or liquid metal may penetrate into the solid metal. This is the liquid metal corrosion. Then a wet or electrochemical corrosion. So wet corrosion occurs under the following conditions: when two dissimilar metals are alloys in contact with each other in the presence of an aqueous solution or moisture, when a metal is exposed to varying concentration of oxygen or any electrolyte. Hydrogen evolution type corrosion. All metals above hydrogens in the electrochemical series have a tendency to get dissolved in acidic solution with simultaneous evolution of hydrogen gas. The diagram is shown in figure. When iron metal contacts with non-oxidizing acid like HCl, H2 evolution reaction will occur. At anode, iron undergoes dissolution to give Fe2 plus ions with the liberation of electrons. Fe, this forms Fe2 plus 2 electrons. Oxidation reaction. At cathode, the liberated electrons flow from anodic to cathodic part where H plus ions reduced to H2. 2H plus 2 electrons, this forms H2. Reduction reaction will take place. So, absorption of oxygen or formation of hydroxide ion type of corrosion. So, the surface of iron is usually coated with a thin film of iron oxide. However, if the oxide film develops, some crack will come and anodic areas are created on the surface while remaining part act as cathode. For example, when iron metal contacts with the neutral solution of an electrolyte in the process of oxidation, OH minus ions are formed. The diagram is shown in figure. At anode, iron dissolves as Fe2 plus with the liberation of electrons. So Fe plus that gives Fe2 plus 2 electrons. Oxidation reaction will take place. So at cathode, reduction reaction will take place. The liberated electrons will flow from anodic to cathodic part to the metal, whereas the electrons are taken up by the dissolved oxygen to form OH minus ions of O2 plus H2O plus 2 electrons, thus forms 2 OH minus. So finally the net reaction of corrosion is Fe2 plus 2 OH minus, thus forms FeOH2. So once corrosion is formed, finally further increased, that forms finally 4 FeOH3. That is also layer of oxide film on the metal. So the difference between chemical and electrochemical corrosion. In chemical corrosion occurs only in dry condition, but in electrochemical corrosion occurs in the presence of moisture or any electrolyte. The chemical corrosion is due to the direct chemical attack of the metal by the environment. The electrochemical corrosion is due to the setup of a large number of cathodic and anodic areas. Chemical corrosion, even a homogeneous metal surface gets corroded. But in electrochemical corrosion, heterogeneous surface or bimetallic contact is the condition. But in chemical corrosion, corrosion products accumulate in the same place where corrosion occurs. But in electrochemical corrosion, corrosion occurs at the anode while products formed elsewhere. In chemical corrosion is self-controlled. Electrochemical corrosion is a continuous process. Chemical corrosion follows adsorption mechanism. Electrochemical corrosion follows electrochemical reaction. Example for chemical corrosion: formation of mild scale on iron surface. Example for electrochemical corrosion: rusting of iron in moist atmosphere. Then types of electrochemical corrosion. Electrochemical corrosions are two types. One is galvanic corrosion, or second one is differential erosion corrosion. The differential erosion corrosion, further named as concentration corrosion, as the same waterline corrosion. The galvanic corrosion, that means when two different metals are in contact with each other in the presence of an aqueous solution or moisture. Galvanic corrosion occurs. Here, more active metal act as anode and less active metal act as cathode. The two examples are shown in figure. The first couple is zinc and iron, and second one is iron and copper. In zinc iron couple represents in which zinc dissolves more active metal, dissolves in difference to iron. Zinc acts as anode and undergoes corrosion, and Fe acts as cathode. In Cu-Fe couple, in which iron dissolves in the presence of copper, that means iron acts as anode, undergoes corrosion, and copper acts as cathode. It prevents corrosion. So examples for galvanic corrosion. First one is steel screw in a brass marine hardware corrodes. This is due to the galvanic corrosion. Iron becomes anodic and it is attacked and corroded, while brass acts as cathodic and is not attacked. Second, bolt and nut made of some same metal is preferred. It is preferred in practice because galvanic corrosion is avoided due to the homogeneous metal. In prevention, galvanic corrosion can be minimized by providing an insulating material between two metals. Second type is differential erosion or concentration corrosion or waterline corrosion. These types of corrosion occurs when a metal is exposed to varying concentration of oxygen or any electrolyte on the surface of the base metal. Metals partially immersed in water, a conducting solution, are called waterline corrosion. The waterline corrosion as shown in figure. The electrode is partially immersed in solution. That is the concentration cell corrosion. One part of the electrode is inside the solution, the other part of the electrode is outside the solution. The metal is partially immersed in conducting solution. The metal part above the solution is more aerated and hence become cathodic. On the other hand, the metal part inside the solution is less aerated and thus become anodic and suffers corrosion. At anode, less aerated corrosion occurs. M that gives M2 plus 2 electrons. At cathode, OH minus ions are produced. That means of O2 plus H2O plus 2 electrons that forms 2 OH minus. Factors influencing the rate of corrosion. The rate and extent of corrosion mainly depends on nature of the metal and nature of the environment. Nature of the metal. First one is position in EMF series. The extent of corrosion depends on the position of the metal in the EMF series. Metals above the hydrogen in EMF series get corroded vigorously. Lower the reduction potential, greater is the rate of corrosion. When two metals are in electrical contact, the more active metal undergoes corrosion. The rate and severity of corrosion depends on the difference in their positions in the EMF series. Greater the difference, faster is the corrosion rate. Relative areas of the anode and cathode. The rate of corrosion will be more when cathodic area is larger. When the cathodic area is larger, the demand for electrons will be more and this results in an increased rate of corrosion of metals at anodic area. Impurity of the metal. The 100% pure metal will not undergo any types of corrosion, but the presence of impurities in a metal creates corrosion and thus galvanic cells are set up with a distinct anode and cathodic area in the metal. Higher the percentage of impurity, faster is the corrosion rate. This is shown in figure. This is shown in the tabulations. If the purity increases, that means corrosion rate will be increased. If the impurity increased, the corrosion rate will be faster. Then over voltage or over potential. The over voltage of a metal in the corrosive environment is inversely proportional to the corrosion rate. Then nature of surface film. The nature of the oxide film formed on the metal surface decides the extent of corrosion, which can be decided by Pilley-Wentworth rule. Then in the case of alkali and alkaline earth metals such as magnesium, calcium, etc. form oxide whose volume is less than the volume of the metal. Hence, the oxide film will be porous and non-protective and bring about further corrosion. But in heavy metals like aluminum, chromium, etc. form oxide whose volume is greater than that of the metal. Hence, the oxide film will be non-porous and protective and prevents further corrosion. The nature of corrosion product. If the corrosion product is soluble in the corroding medium, the corrosion rate will be faster. Similarly, If the corrosion product is volatile, the corrosion rate will be faster. The nature of environment, that is temperature. The rate of corrosion is directly proportional to the temperature. This is because the rate of chemical reaction and the rate of diffusion of the ions increases with rise in the temperature. Hence, the rate of corrosion increases with temperature. Humidity. The rate of corrosion will be more when the humidity in the environment is high. The moisture acts as a solvent for the oxygen in the air to produce electrolyte, which is essential for setting up corrosion cell. Then the presence of corrosive gases. The acidic gases like CO2, SO2 and H2S and fumes of HCl and H2SO4 etc. produces electrolytes which are acidic and increases the electrochemical corrosion. The presence of suspended particles. Particles like NaCl, ammonium sulfate along with moisture act as powerful electrolytes and thus accelerate the electrochemical corrosion. Effect of pH. The possibility of corrosion with respect to the pH of the electrolyte solution and the electrode potential of the metal is correlated with the help of a 4-box diagram. From this 4-box diagram, we have to discuss about corrosion and pH of solutions. It is clearly shows pH. The rate of corrosion of iron can also be reduced by moving the passivity of region by applying the positive metal. From thus, the rate of corrosion will be maximum when corrosive environment is acidic. That means pH is less than 7. Diagram clearly indicates that the rate of corrosion also reduced by increasing the pH values of the solution by adding alkali. In control of corrosion. Corrosion can be controlled in two different methods. First one is sacrificial anodic production. Second one is impressed current cathodic production. Sacrificial anodic production method. In this method, the metallic structure to be protected is made cathode by connecting it with more active metal, so that all the corrosion will concentrate only more active metal. The artificially made anode act as anode and prevents and produces corrosion. Then the original metallic structure is protected from corrosion. Hence, this process is known as sacrificial anodic production method. The diagram is shown in figure. The original metal to be protected from corrosion is attached with more active metal. So, more active metal act as corrosion. So, our original metal is prevented from corrosion. That is the concept of a sacrificial anodic method. Applications of sacrificial anodic method. This method is used for the production of ships and boats. Sheets of magnesium or zinc are hung around the hull of the ship. The zinc or magnesium will act as anode compared to iron. So, corrosion concentrates zinc or magnesium, since they are sacrificed in the process of saving iron. They are called sacrificial anodes. For example, ship is prevented from corrosion. So, ship is made of iron. So, here zinc or magnesium seeds are attached in the iron. So, corrosion will concentrate only more active metal, magnesium or zinc. So, original metal of a ship is prevented from corrosion. So, here sacrificial anodes are zinc or magnesium seeds. So, original metal is prevented from corrosion. That is the concept of sacrificial anodic method. Plus also underground pipelines are prevented from corrosion. So, underground pipelines are also made of iron. So here is also magnesium zinc seeds are attached. So corrosion will concentrate only more active metal, magnesium or zinc seeds. So original metal of underground pipelines are made of iron to be prevented from corrosion. This concept is same as in boiler. So boiler is also made of iron. Here is also zinc or magnesium seeds are used. So these are act as sacrificial anodes. So original metals boiler is prevented from corrosion. So that is the sacrificial anodic method. So thank you.